I think we can begin. Good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Cyber-Physical Systems, IISc. Today's talk is by Dr. Prabhat Gupta, and he'll be speaking on an energy-efficient smart space system using long-range network with security constraint. Dr. Prabhat Gupta is an assistant professor in the Department of Computer Science and Engineering at IIT Varanasi. Previously, he was a technical lead in Samsung R&D Bangalore. He received his PhD and MTech degrees in Computer Science and Engineering from IIT Guwahati. His research interests include the Internet of Things, wireless sensor networks, and human-computer interaction. Before we move on to the talk, we'd like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Gupta or type them in the chat box and we'll moderate it with him. Over to you, Dr. Gupta.
Yeah, thank you. Thank you very much. And a very good afternoon to everyone. And thank you for organizer team for doing all these effort for this event. So today's topic is energy efficient smart space system using LoRa network with security constraints. I'm Prabhat Gupta, and right now I'm at IIT PHU, Varanasi. So this work I have done with two of my PhD students, Preeti Kumari and Rahul Mishra. And one more professor is Professor Sajal K. Das. So they are the four collaborators of this research work. And recently we submit this work in MSWIM 2021 conference, and this work got accepted in that MSWIM 2021 conference. So this paper is available at that conference site. So we start here. So in this talk, we have mainly three sessions. One is introduce about LoRa or the long-range communication protocols. Then we come to our job, our part, that what we have done in this. And the third one is that performance evaluation. We need to measure the performance. If we do this one work, that what positive and negative pros and cons in that one work. And finally, we conclude this presentation. And so very first we can see that, okay, if we want to design and develop a smart environment, a smart space such as a smart office, a smart house, then various protocols, communication protocols are available. So need to think about that, okay, which one is suitable based on our application, based on the network constraints. So if we broadly classify, then we can classify based on the communication range or communication distance, short range communication and the long range communication protocols. So these are some examples of the short range communication, and these are examples of the long range communication protocols. So Sigfox is also comes recently that offer the long range communication protocols, and LoRa 4G, 5G, all are the long range communication protocols where they can communicate some kilometer distance and more than that one. Short range, some meter distance is possible. This is another picture of short range and long range communication. So up to 10 kilometer, of course, more than that one is also possible, these categories. And if we go to the power consumption point of view, then we can see that, of course, this LoRa and other thing comes as a x-axis, that is covers the maximum range, and the y-axis, that is the minimum bound, that means the 1 kbps speed. So this complete presentation is based on the LoRa. So we are here in this presentation. So that means we need to communicate the information as a long range up to 10 kilometers, 20 kilometers, more than that one. But we do not want to consume much energy, much power. So that's why we select this one, 1 kbps. Of course, the other solution is there with respect to the range, but their power consumption is very high, and of course, the data rate is also high. But in the smart home space, we are not required much high data rate. That means we do not want to transmit, in that case, the images and other things or the videos. We want to transmit the sensor data, the sensor values. Most of the cases, that is the binary values, but of course, more than that one. But the size of the information is less as compared to multimedia data and other things. So here our objective is that we want to design a space which is smart. That means they have sensors for sensing the environment. Our data size is very less, but we do not want to replace or recharge battery again and again. That is, we want to cover 7 communication protocol which is suitable. So here we find out our box which is suitable for this one. So if we already classify the communication protocol, one is the short range, other one is the long range. Short range, they consume less energy while transmission, such as Bluetooth or RFID or Zigbee. But the negative point is that short range. In the long range category, they covers the long distance, some kilometers, but of course their energy consumption is very high. LoRa takes advantage of both. That means low energy and long distance. This is known as the LoRa. And LoRa is the physical layer. When we talk about the LoRa, that is the physical layer. When we use the LoRa WAN, that is the MAC layer protocols. These are some demonstration that we have done here nearby the Ganga Ghat for transmission of water pollution monitoring data using LoRa. We also deployed and worked on the agriculture field for deployment of such solutions of the LoRa solutions for finding or monitoring of the events. Now, architecture of the LoRa. So this is the introduction going on the LoRa. So architecture that very first we have the end users. So end users have the sensor and they also have the LoRa device, LoRa nodes. So sensor, they can sense the environment, sense the phenomena, and they attach with the LoRa node, which is known as edge device also. They do some little bit processing and transmit this information to the LoRa gateway. LoRa gateway forward this information to the network server, network forward to the application server, and finally to the end users. So this is a simple example of the architecture of the LoRa node. So in this LoRa system, sensor comes into the picture, LoRa node comes into the picture, network server, end users, LoRa gateway, and application server comes into the picture. What were the properties of the network that is assigned by the network server? Say, for example, in the LoRa SF vector is there, some resources are there that is assigned by the network server. So whenever LoRa node want to transmit some information, they attach with the LoRa gateway attach with the network server, take some resources and transmit this data to the end users. LoRa properties, they support the star topology, which is that means multiple devices, they can transmit their data at the same time, star topology. Bidirectional is also, and they support the unlicensed ISM band, so we are not required to pay cost for the licensed fees and other things. And of course, they use some security protocols that cipher speeding modulation, so they can transmit the data with a low rate but less energy and also secure. But since this is unlicensed ISM band, so definitely people are transmit unlimited, they continuously transmit data again and again, so others people are not able to transmit, need to put some cap. So the LoRa use their duty cycle constraint, so that each and every user, they can transmit up to a certain time. So usually that papers or that work, they say that okay, 1%, 2% duty cycles are enough. So 1% duty cycle means in an entire day we can transmit 864 seconds. So out of 60 seconds we can transmit, out of 100 seconds we can transmit 1 second. These are the LoRa resources, or we can say that perimeters. One is of course frequency, on what frequency you want to transmit. So we have the range of the frequency that we can transmit. So LoRa support that 8 channels, and we can increase that channel up to the 16. Bandwidth, of course their bandwidth is a 125 kbps gap is there, and transmission power range is there. If you increase the transmission power, definitely you can successfully transmit, but power consumption is high. Coding rate, so LoRa also support a different coding rate. So if you want to more secure, then you can go to the 4x5, 4x6, 4x7, 4x8. So that is based on the security, we can increase the coding rate like this one. Speeding factor, for encode the data, transmit this one, and decode the data like this one. LoRa support, of course, right now SF factor 13 and 6 is also there. So usually LoRa support SF factor 7 to 12 speeding factor. SF factor 7 is suitable for the nearby devices. If LoRa gateway and LoRa device distance is less, then we can use the SF factor 7 as compared to SF factor 8. Moreover,
can I interrupt for a minute?
Yeah, sure.
So just the previous slide you were mentioning, you could change the coding rate to improve security. You mean security or reliability? Just want to make sure I'm following. Like security meaning prevent from eavesdropper, or just make sure the information can be transferred reliably?
Yeah, so coding rate is directly related to the reliability, because coding rate means
so you're talking of reliability, not security. Just want to make sure. So
yes, reliability.
Okay, thanks.
So 4 by 6 means 2 bits for the, that means, yes, you successfully transmit or not, that means reliability. So here SA factor 7 to 12, SA factor 7, that means the device and the LoRa gateway are nearby. SA factor 8, increase the distance, we need to increase the SA factors. But yes, SA factor 8 takes more time as compared to SA factor 7. So SA factor increase, that means you compromise with the data rate. So you need to, if you want high data rate, that means you need to use the SA factor 7 in place of the SA factor 8 or the SA factor 9. But so if the distance is more, you are not able to use the SA factor 8. SA factor 7 is suitable for this. So both settings are there in the LoRa. Either you can manually you can set, or adaptive data rate is ADR is also there. Then in that case, the network server LoRa gateway, they can assign the SA factor based on the RSSI values. But we go to the challenges, that what challenges are there. If we go to the literatures and find out the challenges, one is the limited resources. So you have SA factor 7 to 12, but some people they say SA factor 6 and SA factor 13 are also there. So definitely they have the limited channels, not unlimited virtual channels. So channels are limited. That means this is a resource constraint. Parallelly, up to a maximum number of devices they can transmit. So with the combination of frequency and the SA factors, you can find out the parallel devices transmission. Data rate is also very less, that 27 kbps data rate maximum possible. This is the digit that is around kbps, and which is the less than or equals to BLE Bluetooth, not even Wi-Fi. So we are not assuming that we can transmit some huge data in the LoRa. That is the second challenge. Of course, the third challenge is the free spectrum. So everyone wants to transmit their data as much as possible, but in that case, definitely congestion comes into the picture. So for data rate is that means the data rate and the limited free radio frequency band is also a one challenge. And the security is also a challenge, because when we send the data, then most of the devices are the edge device or the light processing devices. We are not assuming that the one bigger size or complex encryption techniques you can use as the edge device or as the sender node or the sensor node or sensor device. So security is also challenging. If we assume that the sender is a very strong machine, then you can encrypt it, you can secure as much as possible. But here that is the challenge, because the data transmitted using the edge device. Our main concern is the battery powered devices. So these are some solutions comes into the picture 2019 onwards. Okay, what other people are doing for solving this one problem. So for the interference problem, if we have the interference, that means a large number of devices that try to transmit their data. So definitely the interference comes into the picture. So the theoretical point of view, the LoRa use the multiple speeding factor. All the speeding factor are orthogonal. That means SA factor 7, there is no interference with SA factor 8. But practically there are some interferences there. So that's where we divide the interference into two categories. One is the co-SA factor interference, other one is the inter-SA interference. So between SA factor 7 and SA factor 8, and the interference within the SA factor 7 and SA factor 7, if two devices transmit the same data, same frequency, then definitely interference. 2019, the solution comes into the picture that, okay, you can divide the time slot with a fixed time window for each node, that this device transmit at time t, other device they can transmit at time t plus 1, like this one type of combination. But these combinations are also not suitable. Why? Because these are the nodes, sensor nodes. So whenever they have the data, they can transmit. We are not able to pre-plan, or we are not able to fix the that, okay, this node transmit at time t, this node transmit at time t plus 1. So unnecessary, you reserve the slot for a particular device, and device they have no data. So unnecessary, unused resources are there. You are not using the proper resource utility in that case. Another approach is the modulation technique. They use the different modulation technique for reducing the interference problem, but it is also suitable up to the limited nodes. If more than nodes are there, then definitely demodulation has the noise and also takes time. Low power signals is that means if you want to reduce the interference, then some devices they reduce their power signal system. So definitely high power signals they can transmit their data. But this solution is also approximate solution. Everyone wants to transmit, everyone is greedy. So this solution is also practically has some challenges in that case. The second is the data transmission problem. We are not able to transmit much data because of the data rate. So that 2019, they proposed one method that's selected transmission. You are not required to transmit all the information, only your crucial information you can transmit. So in that case, sometimes we miss the crucial information. We assume that, okay, we can transmit the average of these values or the mean of these values, but definitely we can miss some peaks and other things in that case. So that is the solution also have the challenge. Other work comes into the picture, the compression. So before transmission, you can compress the data, but whatever the paper proposed or whatever the work is there, they are not considered the LoRa property with the compression. That means they cover the two different approaches. One is the compression, other one is the LoRa protocol. Whatever the compression technique, they default use the compression technique. They are not considered the data rate or SF factor and other things. So that type of challenges is there. So duty cycle and the duty cycle with the duty cycle, the papers, they are not considered the duty cycle because of the simulation results and other things. Or some paper they consider a large duty cycle. So they assume that, okay, duty cycle is sufficient like this. So these are the challenges that we observe in the LoRa network and find out what existing solutions are there. And these are the solution approaches. Now we come to our job that we consider a scenario where some houses are there. These are the house, they have some appliances. So appliance generate some values, some sensory data. We assume that multidimensional time series. Say for example, the voltage degree. So if power consumption is there, so these are the power consumption waveform of first device. This is another appliances. This is the other appliances. This is the other appliances like this one. So these are the appliances. Their power series is there. They generate some power consumption like this one. This is another house. They also have other devices or other appliances. They generate the power series. We have one edge device. Edge device is there. So what they are doing, they encrypt this data based on their processing capability and capacity. So they encrypt this data and they also compress this data. So compression and encryption is there. We do the compression so that we can transmit the data within the available resources. So here, while we use the compression, we consider the resources. And during the encryption, we consider that what encryption level is required. So assume that my data is not very much important and the attacker is not interested in unnecessary data which are not important, which is not generate the money. So we are unnecessary. We are using a high encryption technique. So say for example that AES, we have the rounds are there. If we increase the rounds, definitely we can increase the security level sort of thing. So unnecessary, we increase the time complexity or computational complexity of the encryption algorithm. Even my data is not important, or we can say the attacker is not there like this. So if we assume that the data is important and the vulnerability is there in the network or some attacks are already there, then definitely we need to use a high-end encryption technique. So our encryption technique, whatever the encryption technique used in this smart space, based on the strength of the attacker and also the importance of your data. And the compression depends on your resources availability, that what resources are there. We compress at that level. Once the compression and encrypted data, we transmit to the LoRa to the network server. Network server attached with the application server. First they decrypt and then after decryption. So this is the mechanism that the smart home, that means smart space scenario they have. So generate the data and compress the data, encrypt the data, transmit the data, decrypt the data, and decompress the data so that the original data is here at the receiver side. So in this work, we address the following problem, that how securely transfer the multidimensional time series to the application server in a given time duration with the minimum cost of the security mechanism and energy consumption. So we have various constraints here that say, here first we consider multidimensional time series, not only one time series. That means the time series are there. And whenever we talk about the multidimensional time series, at the center side, we also assume that we can find out the multidimensional time series after decryption and decompression. Okay, so compression and decompression, that means both are the reverse we are required. And also we want to reduce the cost of the security mechanism. So we can save the energy and the power and the time of the edge device if we use the less complex or security mechanism. And we also reduce the energy consumption. So we do not want too much rounds here at this level for the transmission. And of course, the secure communication is required. Because of that reason, we use the security mechanism. So security, time constraint, minimum cost of the and security and the energy, these are our challenges in this problem. And we find out these challenges and try to solve these challenges in this problem. So this is the solution architecture, that sensors, they generate some sensor values. These sensor nodes are attached with some node, their processor, they can transmit this. So they generate the multi-dimensional time series. First we compress, then after encrypt, so that we can reduce the time complexity of the encryption. If we already compress the data, that means my number of elements are less for encryption. And then we use the transmission, then reverse, the same thing. That is the architecture that we have used for the solution point of view. So the solution, they have the 3 steps. First, the compression, then after secure the compression. And we also estimate the energy, delay, and the cost of the system. And we select the perimeters of the network which provide minimum energy consumption, less delay, and the cost of the system. So we merge all these three things in the one, and this is the solution. That is the final solution. So the contribution, first we design a one compression decompression, that means encoder and decoder using DNA network. Then we secure using game theory. And finally, we estimate the energy, delay, cost of the system. And we select the network parameter which is suitable or which gives the minimum energy consumption, and the delay is less than whatever the delay we are assuming, and the cost minimizes. So the step one, compression and decompression model. So we need to compress. So this is the raw data, whatever the sensory data is there after pre-process. And we use one compression model, or just opposite the decompression model. These are the mirror images. That means, and this compression runs at your node side, and this is your application server side. That is for decompression. And since we assume that this is the smart home, we have some data. If you have no such data, then you can use, then in that case, we assume there's some transfer learning sort of thing. We can take the data from other apartments and use that data for the training purpose. These are the LSTM cells, so that we can make the correlation between sensor data. That means we can make the history of relation of these elements. So we use the LSTM memory cells here. And so at the initially we generate these data. After this exercise of the compression, we have this data size. So the data size is less than the original data size. And once again, we transmit this data. And after transmission, we regenerate this one data. So this is the compression part, and this is the decompression part. So indirectly, we can say this is the encoder, and the just opposite side, this is the decoder of that one data. So objective is that to minimize the error. So here we consider the two types of the error. One is the average or the mean error. Other one is the variance. This is the first order. This is the second order. So we consider the first order statistics and also the second order statistics. So variance is also there and mean is there. So first we calculate the from whatever the value of at the first layer, and what is the difference between 2Q. 2Q is the last layer value at the receiver side, and this is my sender side first layer. This is the last layer of the receiver side. Difference between these two time series, this is our objective. We want to minimize this one in this. So at the time of training, we train the model in such a way so that this loss is minimized. Here we consider both type of loss, that means both type of error. One is the mean and also the variance. So this is the variance difference, this is the mean, and here we give the weightage of the variance and also weightage to the mean values. This is the loss function. Objective is to minimize this loss function. Initially, we have done some experiment that we consider only the mean, but we are not able to find out the result accuracy, high accuracy. Then we go to the mean, so variance direction. And once again, we use only the variance, then also not because they miss some mean values in that case. So we consider both mean and variance. Lambda is one hyperparameters. They're moving on again and find out a suitable value of the lambda, which gives the less loss or the error. So with the help of this exercise, we can train the deep neural network. And here we use layers, LSTM layers. So this is the mechanism that we use for the compression of the time series, whatever the time series is we generated. After compression, we need to secure the time series. This is a very interesting part. So assume that there is one attacker is there between from your LoRa node and the LoRa gateway. They try to attack your data and or modify their data. And this is the smart space user. They generate some data. So smart space, they have two options. Either they can secure their data or they do not want to secure their data. Okay, there are two options are there. They want to secure their data, they do not want to secure their data. Similar is the attacker, they also have the two options. They attack on the time series, they do not want to attack on the time series. So in that case, we have simple two-player game is there, and each player they have the two actions. So we have some payoff and with some cost metrics. So here we can see that the cost pay by the attacker for the malware software or some attack virus is there. So they need to pay this cost if they want to attack. If they want to attack, they need to pay this one cost minus CNA cost for the attacker at the nth smart home. This is the N indicate the smart home, nth number is smart home, and A indicate the attacker. If we are not using the superscript, that means this is the user matrix and this is the attacker matrix. And alpha N is the probability of the security of the compressed MTS. So usually we want high alpha. That means our expectations is 100% alpha, but 100% is not possible. That's why because of the loss and other things. So if we consider some probability alpha lies between 0 and 1, but as high as possible. Alpha is indicate the security, 1 minus alpha is indicate the unsecured transmission. So if the attacker, they pay this one cost, CNA cost for this malware software purchasing and other thing. Of course, the attacker, they have the gain. The gain is the profit of the attack if they attack on this time series, if they can successfully attack on this time data. So alpha is the security, 1 minus alpha is unsecure multiplied by whatever the gain is there. So this is their payoff of the attacker. If they attack on the time series and they get some reward sort of thing. If the user or the smart space user, if they use some security mechanism, first thing they need to pay some cost of the security. They need to pay this security software if they use some antivirus, some sort of thing. Here we consider the security cost in terms of the processing, how many number of processors, processing power they require, how many number of loops are running. So this is there. 1 minus alpha, alpha is the security, this is the attack, and LS is the loss. Whatever the loss is there, of course, their loss is there if they are not able to successfully protect themselves. So definitely their loss is there. So the users, if attacker is there, definitely they need to purchase some antiviruses or some security mechanism. And also they need to have some loss if they are not able to successfully attack, even they purchase it. If a user, they have no such antivirus, some sort of thing, definitely if attacker is there, they can attack and your alpha n is equals to 0. Because the attacker is already there, they try to attack and you are not using any security mechanism. So in that case, we can simply say that the alpha n equals to 0. Of course, here these smart users, they are not required to purchase any antivirus or any software in that case. So they are not required to pay this CN cost here. Similar as this one attacker, that alpha n equals to 0, then they have this payoff like this. Other metrics also we can fill with the help of these variables. We can find out this one. Now we go through that one and we check that we are not able to find out the Nash equilibrium. That's why we need to go through the mixed strategy of the Nash equilibrium. That means that there is no dominant strategy. Then we think about the mixed strategy. X is indicate this one x1, 1 minus x dash is 1 minus x. And so same as this one is. So if we write the mixed strategy of the Nash equilibrium for a smart home point of view, we can consider this one matrix. And if we use this one matrix, put some values of this one payoff matrix, we can easily find out the alpha. Alpha n indicates that the probability of the security. In terms of the cost, what cost that the user need to pay for the security purpose. So this alpha n indicates in terms of the CN and LN. CN is the cost for purchasing the antivirus software or your security mechanism. LN is their loss, whatever the loss is there. Similar as the attacker. If we go to the attacker strategy, Nash equilibrium, mixed strategy of the Nash equilibrium, we can find out this type of equation. And once we solve or put all these values, we can find out alpha n equals to like this one type of the matrix here. Now we have the 2 alpha. So this is the security and that is also a security. So of course, if we have the 2 in the mixed strategy, we can consider the minimum of this components. So this is your resultant security, whatever the security is there. So if attacker is there, and if defender, if you use the security mechanism, not use the security mechanism, whatever is there. So we find out finally this. Here we use some non-linear function for ln and this non-linear function. We put non-linear function for the loss and the gain. Then finally we find out this lemma. This is the in terms of this constant in terms of the alpha and security. So if a user, they already give that whatever I want to transmit, I transmit with the 90% security. So you need to pay this cost. So this cost in terms of the number of loops, number of processing power, what processing power or what loops are required for security purpose, they present in that way here. So this is the lemma that we find out. Now we just skip all these mathematics. Here we have the mathematics for calculate the time for compressing the data, because when we compress the data, we use the deep neural network. So here we use the number of layers, number of neurons mathematics, and with the help of number of layers, number of neurons per LSTM cell, what time complexity is there. If we consider, if we put all these mathematics, we can easily find out the time required for the compression of the data. Similar as for the security purpose, whatever the time required for the security. For here in this paper, we use the AES algorithm for the security. And here the waiting time is also an interesting, that whenever a node they want to transmit their data, they need to wait if their SF factor is not available. That means SF factor is already occupied by others. So you need to wait for some time. And this is the waiting time. If the SF factor is free, then we are not required to wait for that one time. And the communication delay, whatever the delay, based on the SF factor, we can calculate the time duration for transmission of the data. And this communication delay is also depend on your compressed data size. So here we have the mathematics where the one variable is also there, which indicates the size of the compressed data. in the communication. Security cost indicate that how much number of loops you are required for the security. So this once again we skip this one. This is the final equation. So in this equation we use this alpha because alpha indicate the probability of the security. You need this probability. That means you need this type of the cost in terms of the computational complexity. Energy consumption depend on the delay and because you transmit the data. So whenever you transmit the data, you consume the energy. Whenever you compress the data, you also need to consume the power consumption. So power consumption indicates the compression time, security time, and the communication time. So here we just simply write the variables, but each variable they have the bigger equation. So we need to solve this. So here finally we have the three matrices. One is the delay, total time required for compression and security transmission, and for security cost and for energy cost. Now once again we go the first slide of the second section, that what problem statement is there. So the problem statement was how securely transfer the multidimensional time series to the application server in a given time duration with the minimum cost of the security and the energy. That means you want to minimize the energy and the cost of the security if we encrypt the data. And of course, in the system, we have the n smart houses. So that's where we use the integration or summation of the n houses. And we give the weightage for the security as well as for the cost of the encryption. And here, these are the threshold that you want to security more than the threshold, whatever the threshold is given. That means we already given that at least 90% data must be securely transmitted. So this is your threshold. And you also set the time duration. You need to transmit. Transmit means for compression and also encryption and transmission, all these three duration, and the waiting time also there. So here we calculate this one time delay. So delay must be less than the given time duration. So if you already given the cap of the maximum time duration, then data need to transmit within this time duration. And of course, one more constraint is there. Successfully transmit means your accuracy is high. At the time of when we decrypt the data, when we decompress the data, original time series, we expect that we find out the same multi-dimensional original time series, whatever the time series that we generated at the node side. So accuracy, we need as high as possible, at least more than the threshold value, whatever the threshold value is there. So this is the optimization equation where we convert this one. We already calculate all these variables in terms of these parameters, alpha and other things that we find out. So we divide the solution into two levels. One is the lower level, other one is the upper level. So lower level means that you already fix the SF factor, that you know that I want to transmit on SF factor 7 or SF factor 7. So this solution gives the data size, but data size is suitable, which gives all these parameters. That means they satisfy your accuracy. They also give a security level, and the time consumption is less than the threshold values like this. So here we use the Cushing-Newton method because that means if we use the normal method of the Newton method, then definitely the complexity is high. Here we want to reduce the complexity, and also Jacobian matrix as a matrix calculation takes time. So that's why we use the approximate solution, and we also assume that the fixed SF factor is already given. Based on that one, we can do the exercise. Now this is the upper level. We vary the SF factor, whatever the SF factors are possible. So we consider all the combinations of the SF factor, and the solution that we propose in this procedure one, we call the procedure one in this site for a specific SF factor, calculate that values and find out this one. So here the lemma one calculate alpha n, that we already seen that the alpha n we calculate with the help of lemma one. And here the procedure one gives the data size, what data size is suitable for this security level, and this loop indicates that which SF factor is suitable for transmission of data. Once we find out this system coefficient, where that means you can transmit this size of the data, you use this one SF factor, we use for the future purpose for transmission of the data. So this is the outcome of this complete exercise, what exercise we have done. So we repeat, that means for the performance evaluation point of view for this one, but we use the extension of the NS2 NS3 simulator, and we use the KSAS smart home datasets. Yes, the KSAS have multiple scenarios of the smart home where 1 BHK, 2 BHK apartment is there. They have the multiple time series of the data for sensor data and power consumption data also. And we use the DNN, that LSTM for compression and transmission. Here the frequency, we use this one frequency, and the bandwidth and range is there. Energy consumption we consider for the ideal 2, and for transmission 32 microjoules. Like duty cycle we consider 1% duty cycle, and performance matrices. First we check that okay, what compression size is there. because that compression size is suitable for the accuracy also. And also data. If you more compress, you can reduce the transmission time, but it is very tough to regenerate the same time series. If your compression is high, so lossless compression is not possible. Definitely some loss is high, but of course we can save that time while transmission of the data. So this is the important metrics. Then after we find out the delay metrics and energy consumption and accuracy. So these are the performance metrics that we consider in these results. So these results are quite a bit interesting. So here we can see that if we increase the compression ratio up to 20 to 80% or 90%, we can see that the delay goes down and down because we compress data and transmission takes less time. And of course, security protocol encryption also takes less time because encryption needs less data for encryption and looping purpose. So if my DTS delay threshold says that, okay, we can tolerate up to this one level of the delay. That means if you compress more than this one, that is suitable as a delay point of view. If you transmit, if you compress 20% compression, then that takes more time for transmission of the data. If we consider 22% or more than 22% compression, this is suitable as a delay point of view. That means communication delay is suitable for this one. So total delay is less than whatever the delay threshold is given. So as a delay point of view, this range is suitable. But if I compress more than the 70% compression, then we are not able to find out the desired accuracy. We can compress only up to the 70%. If we compress more than that one, we are not able to regenerate the same time series, whatever the time series generated by the smart home. So that means directly, indirectly, the feasible range is between 25 or 22 to 70. So this is my feasible range with respect to the delay and the accuracy. We also need to consider the energy consumption and the cost. So if we compress this one, we calculate the energy consumption graph comes like this one. Okay. You compress more and more, you require the less security energy consumption while securing the data and also while communicating the data. So here we can also save the energy. And for the cost point of view, we can reduce the cost ratio, but after a certain time, if you compress more and more, definitely your cost. Cost means the security cost. So if you have the less data, you need to pay the less security cost because you are required the less number of loops of the security point of view. But a very, very small information, definitely your cost drastically high because of the softwares, they have some package sort of things. So after a certain size, they take the prices of the constant price like this one. They are not proportionally reduce the prices as the sizes. So up to the certain threshold values, they reduce the price, but after certain they increase the size. So here we can find out that, okay, this is the window where we can select the compression ratio between this and this. And based on our optimization function, we can find out which one is the optimal value, minimum value of this one. So the algorithm automatically calculates this one value, or they can give the answer, but we also use the checkpoints in the NS2 and NS3, and we find out these type of the results and graphs, and we find out, okay, this internally they are doing like this one, and we find out that result only this one window is suitable window for our calculation purpose. So with the help of this result, we observe that a low compression takes ratio takes more time, and the high compression ratio does not provide the desired accuracy. So high compression ratio accuracy compromise, low compression ratio takes more time. Another result is that with respect to constraint. So if my time window is like this one and this one, so here we can consider the delay, whatever the delay is there. Of course, when we compress more and more data, then delay goes down, but accuracy also compromise with this one. So we find out this one window that we already seen that. Here the accuracy is also there. If we want accuracy 90%, we have the more window threshold. If we want to accuracy up to this one 95%, that we have the window like this one. So we have the two windows. If we delay threshold is 80%, my window is this one. If someone said that the delay is 40% delay, then window is only this one. So here that means these parameters, they give a less window for selection of the perfect value of the compression. So here in this graph, in this result, we want to find out these type of conclusions that, okay, if you have the more flexibility, then you have the more window for the selection purpose. Similar is the alpha, 95% accuracy, 90% security level, 95% security level, and 90% security levels. This is the another graph for perimeters of the game theory parameters. So if this alpha n, indicate the cost that is paid by the user for antivirus purpose or the security mechanism. So whenever you want more security alpha n, then definitely you need to pay more cost. And after a certain threshold, you need to pay very high cost for the security. And similar is that one, that Cn is the cost of the antivirus that that attacker, they purchase this one virus attack, so they also need to pay more cost if you want more securely. That means you have the more secure mechanism. So definitely attacker need to pay more cost like this one. So these graph also indicate that of course when we select the perimeter that alpha n, then we need to pay the more cost if your alpha n requirement is high for the security point. So after this exercise in NS3, we find out the result and we fix the perimeters and find out the perimeter. Then we try to implement the same thing as a prototype inside the lab. But here in this prototype, what we are doing, we do the reverse engineering sort of thing. We have the scenario, we have the data set. We put the data set in the simulation. We find out the exact compression ratio, SF factors, and loop, how many number of loops are required for security. And statically, we put all these things in our hard-coded program here. And here, data set point of view, we use the Kesas data set and put the data set on these nodes. Okay, and try to transmit this data to the LoRa gateway to the network server like this. So in this experiment, this is not the complete prototype solution. I will not say that this is the prototype solution because we do the reverse engineering. First, we calculate all the perimeter with the help of simulation. We take these perimeters and put hard-coded that perimeter in the hardware and check that whether it is possible or not. That means whatever simulation is doing, whether it is possible or not, we successfully transmit the data or not. First thing, what is the loss of the data? What recovery of the data when we regenerate the time series, whether we are able to regenerate the time series or not. So all these things are there. So we do the prototype and we find out that yes, we successfully transmit the data, successfully all these things. And here, this LoRa gateway, we consider the single channel LoRa gateway because we use the same IC as the node as a LoRa gateway. So this is the single channel. So we already fixed the SF factor 7 while transmission of this data like this. So because we already find out the SF factor with the help of simulation, we fix that SF factor at the center side as well as the gateway side. And so this is the single channel, that means only one SF factor they support, not the multi-channel LoRa gateway. So this is the mechanism that we have used for the correction purpose or for the checking purposes that the work is working on. So in this work, we design a energy efficient smart space so that we can successfully transmit the data with a minimum cost solution and of course the energy efficient, secure and other things. Here we are not considered the fault tolerant network. Maybe possible LoRa gateway is not free, there are the switch off or some problems are there. Then we also need to consider the multiple LoRa gateways. That mechanism we have not considered. So, and also we are considered the mirror image of compressor or decompression model. So that we also need to do some exercise here and there because these nodes are very lightweight nodes. We are not assuming that heavy DNN models can run at this node, definitely here. So that we also need to rethink about the compression model at this point of view. So there are two feature work that we are doing here in the exercise point of view. So maybe possible to find out a much better result in this case. So thank you very much for this is all about from my side, and this work is accepted, and I think that the paper will come very soon on MSWIM conference portal. Yeah. Thank you very much.
Thank you, Dr. Gupta, for the wonderful talk. We have one question from the audience, which was, are there any implementations of LoRa in the real world? That is, where can we find real world deployments of LoRa?
So here one single channel we try to deploy the single channel in our smart apartment, door open, door closed, my office itself, that okay, if a student is comes in my office or not, that single channel we have done. And recently we set up the multi-channel LoRa gateway also, the TTN outdoor gateway, that if you go to the TTN portal, then you can find out that in India there is one gateway, so that in the Varanasi region, that is the outdoor gateway. So that type of solutions are going on. Previously, there are these gateways and other things are not support this one frequency, because in India the free license spectrum band is the 865 to 67, but this LoRa they support the 868 like this one. So that one is the problem, and of course the hardware and other things problem. But right now that scenarios are very, because the hardware is very cheap. Right now the hardware cost is very less, so definitely the solutions are there. So here I try to deploy some nodes for monitoring my own office, that if students are coming and if they are sitting on their seat or not, if they sit, that research is for how much time and what, that type of exercise. And also we deploy in our apartment the same thing. So that exercise we have done, but of course this is only the experimental point of view, not real-time deployment. So that plus point is that right now the cost is very less. So one LoRa node, they need a one controller. Either we can use the any Arduino board that and one LoRa IC is required. Mainly two components are required, and so the cost is around, if we design in-house one PCB board, put all these things, then cost is around 1,500 rupees per node. It's a very less. And if you use the single channel LoRa, of course, that is not LoRa WAN gateway, that is the LoRa gateway, we can say. So that cost is the same as that one, because we can use this node as a gateway also. And if you go to the multi-channel gateway, then indoor cost is also around 10,000, outdoor gateway is 70,000. So right now the cost is very less. So definitely we expect that near future we find out various solutions or scenarios in this direction. Yeah, please.
I hope that answers Karthik's question. If you need any further clarifications, you may please ask Dr. Gupta.
AR, that is one, yeah, when I got a one chat, one point that smart home point of view, yeah, that LoRa support a very low data rate. That is one problem. So that means AR, VR point of view. So we discussed with our multimedia group. That is the one solution that we figure out that if we have one camera monitor the face, they detect that one, all these things they can do, and they can transmit only the result. Yes, this ID of the user is like this. So we are not required to transmit the image for the face recognition. If you recognize the face, you can identify the person, you can transmit only the ID of that user. That ID of the user we can transmit with the help of LoRa, but of course the AR, VR or that type of heavy image, the data rate is support is not possible in that case. Yeah, and yes, I think so. And that is and placing a gateway edge locally at the home itself. Yeah, that. So placing a gateway at the or the edge locally at the home. Yeah, it is possible that indoor LoRa gateway is also there. TT and indoor LoRa gateway, their cost is also very less, around 10,000. Only the problem with that one that they covers a very less range. And of course, inside outdoor LoRa gateway cost is around 70,000. Recently, I purchased last week, so we already set up that gateway. So their cost. So right now we can place indoor and outdoor, both options are there. And in terms of the multiple networks, so reduce the complexity in terms of the multiple networks. So multiple network. See, if you have the outdoor gateway, one gateway is more than sufficient for entire network, because we already have the cap of the duty cycle. We also need to transmit a very small size of the information. So network load is already very less in that case. Yeah, sure. And please, any other query? 865 to 867, there is one more that is the message there. So only 2 megahertz bandwidth. So more. So these 2 megahertz there, but we need to divide once again the frequency 125 kilohertz. So 865, 165, 865, 165 multiplied by 2. That type of sub bands are also there. So there is no only 2 megahertz. We have the multiple, because every time we 125 kb we can plus. So there are the multiple frequencies and also multiple channels. That means you have the SF factor 7 to 12, and these combinations are also there. And these are the sufficient, because the LoRa need to transmit only 0 and 1 information, door open and door close. So when you transmit, others are not able to transmit, but your transmission time itself is very less. Yes, please. Hello.
Yeah, so we have another question. Is there a trade-off between data rate and range of communication?
Yes, range of that SF factor 7 that have the that high data rate, but their communication range is less. SF factor 8 is the low data rate, but their communication range is high. So if you want a high communication data rate, then you need to use the low SF factor. SF factor 7 is suitable for high data rate, and but their communication range is very less as compared to SF factor 12. So if you want a low data rate, you can go up to the long distance. Any other question is there? I think so. We already discussed all these questions. Yeah.
Yes. Are there any other questions? Okay, if there are no other questions, I think we'll end the session here. Thank you, Dr. Gupta, again for the wonderful talk. And as discussed before, we'd like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details, and the links have already been pasted in the chat box. The link to the recorded video will also be posted on the webpage. Thank you and have a great evening.
Thank you. Thank you very much.